you for the opportunity to speak here. I'm very happy to be here. Give you this very introductory lecture to complex hyperbolicity and the reasons why jet spaces and non-reductive quotients appear in this year here. So first of all, let me recall the very general picture that we would like to, so conjectural picture that we would like to prove in this field of complex hyperbolicity. And everything is based on what would morally be the classification of complex varieties. So recall that, as is well known, in dimension 1, if you take X, a complex projective curve, a lot of properties are determined by the genus of X, which is an invariant, which can be 0, 1, or higher than 2. And in this situation, there are many properties that differ widely from one class to the other. So I won't recall all of them, but for example, recall that X tilde, the universal cover, is either P1, C, or the unit disk. And there are many, many properties that express, generally speaking, that you have here a class with positive curvature, zero curvature, and negative curvature. And this is this picture that we would like to extend to higher dimension when we talk about classifying complex projective varieties. So how do we do that usually? Well, we introduce the notion of Cadorel dimension. So let X be a complex projective manifold, any dimension. Then recall that we have an invariant which is called the Cadorel dimension of X. So this is an element which can be either an integer or minus infinity. So it's either minus infinity or some integer varying between 0 and the dimension of X, which classifies, which characterizes the growth of sections of power of the canonical bundle of X. So, such that, if you consider the dimensions of the spaces of sections of the canonical bundle of X, then this growth morally as m to the power of this Cadorel dimension. At least if m is divisible enough. Okay, so if we go back to the case of curve, then it is well known that you have minus infinity for the 0 genus, 0 for the genus 1, and 1 for the hyperbolic curves, that is the one that have genus higher than 2. Okay. So you see that here you have three classes, one which is very much larger than the others, and usually we say that a complex manifold is of general type if its Cadorel dimension is maximum, equal to the dimension of the variety. So, for example, for surfaces, if you remember Cadorel classification, we are able to classify surfaces which are not of general type. So you have many different classes which corresponds to the value of the Cadorel dimension actually. So I won't recall all of them, but you have the ruled surfaces, the K3, the Enriquez, and the abelian varieties which have Cadorel dimension 0. You have also other bielliptic curves, surfaces. And for the ones that are of general type, well, we cannot say much. These are all the atoms. Okay, so one of the purposes of complex hyperbolicity is to try to better understand this very large class. And it proposes somehow an alternative proposition for classifying complex variety, which is based on the properties of entire curves. So let me define what is an entire curve. An entire curve in X well, it is a non-constant holomorphic map from C to X. Okay, and so let us get back to the example. Oh, sorry, my table is quite low on the board. But we can ask ourselves if there are entire curves inside X. So, of course, if X is P1, then you have many entire curves inside P1. You can take, for example, the affine space A1 inside P1. So, yes. Now, if you have an elliptic curve, since this elliptic curve is covered by C, then, of course, the uniformizing map provides such an entire curve. So you have entire curves, you also have many of them. And if the genus is higher than 2, if X is a curve with genus higher than 2, then you don't have any entire curve. On X. So the proof is very easy using the uniformizing theorem. So you know that if you take X, then it is uniformized by the disk. And so any map from F to X will lift to the disk, giving you a holomorphic bounded map. Which is constant by Liouville theorem. So you cannot have any such non-constant map. So the answer here is no. There are no entire curves. So you see that you have this kind of dichotomy between the curves which admit and the curves which don't admit such entire curves. And so in complex hyperbolicity, we have conjecturally moral classification of varieties depending on these two opposite sides. So I will present these two conjectures, which are due to Green-Griffith length on one side and Campana on the other side. So to introduce this conjecture, sorry, I forgot line here. To introduce these two conjectures, I will need to define one of the sides which are illustrated here. So you see here you have this dichotomy between the curves which are general type and the ones that are not. So in higher dimension it will not be as simple, but one side of the conjectures will be realized by varieties which we call of special type, or special varieties. And I need first to illustrate Campana's conjecture to recall a bit of his theory of orbifolds and special varieties. So in this setting, what we call an orbifold, so it's not a Stacky orbifold, it's an orbifold in Campana's terminology. It is simply a pair X delta with delta the sum of prime divisors, finite sum of prime divisors on X with simple normal crossing support. I will pick X smooth, so it's if you take only the support of delta, you get a smooth log pair. And the AI are rational numbers between 0 and okay, so how you get a K80 pair. And then we say that an orbifold X delta is of general type. General type, sorry. If, so we have the same property as here, actually. So I will not write the full definition, but I will explain orally what it is. If, when you consider the Cadorel dimension of the canonical bundle of X plus delta, it is equal to the dimension of the variety itself. So what I mean by that is that if you plug that here instead, take kx plus delta to the power m, you have the same growth, but here you have the dimension of X. Okay, so we say that we have an orbifold of general type if you have this condition. And now we say that smooth variety, say projective variety, is of special type. Only if it cannot fiber above a variety such that the orbifold base is of general type. So if for any, say, rational fibration, so by this I mean a rational morphism, which is birational to a fibration, such that the base is of positive dimension, then the orbifold base is not of general type. So this is not exactly true, but I will precise that just in a moment. But first, I want just to explain what is the orbifold base. So imagine for a moment that F is a true fibration, it's not a rational fibration. Then inside Y, you have prime divisors above which F ramifies. So take a component D, for example, here. And above that component, you have several components that are sent to it. And on each one of them, you have a multiplicity, Mi, for the fibration. Then you simply put on D the multiplicity, which is given by a standard form, 1 minus 1 over such an integer, which will be the maximum of all the multiplicities. Okay, so here, usually if you wanted to do a stacky situation, you would use a GCD here. Sorry, rather an LCM. But here we put the maximum, which is one of the situations which is described by Campanas theory. Okay, and then I lied a bit. This is not true for any fibration, but possibly after changing the model of the fibration. So if I put X here, then maybe you have to change the model to get a true fibration such that the base is not of general type. It can happen that the Cadorel dimension decreases when you change the model, and so that is what you have to do. Okay, and now I can express the two conjectures of complex hyperbolicity. So first of all, we have the Green-Griffith-Fang conjecture. So we put here. So the version we use now was rephrased after work of Griffith by Lang in 87, if I'm not mistaken. So what does this conjecture tell us? So take X, a complex projective manifold. Then there should be an equivalence between, first, the fact that X is of general type, and secondly, the fact that inside X there exists, I will call it Z, an algebraic subset containing the images of all entire curves inside X. So such that for any map from F from C to X, holomorphic, if this map doesn't fall into Z, then it has to be constant. Okay, so this is the first conjecture, and I will say orally that if this conjecture is true, then it has an implication that if you take the Zariski closure of all these images, then you get an algebraic proper subset, which also contains, for example, all the subvarieties which are not of general type. So this gives a conjectural strong structure theorem for varieties which are of general type. And on the other side of the picture, you have a conjecture which is due to Campana. So, same as here, take a complex projective manifold. Then there should also be an equivalence between, first, the fact that X is of special type, or special, and on the other hand, the fact that inside X there exists an entire curve, a non-constant holomorphic map, with dense image. So you can make two conjectures, either with Zariski, or you can even ask Euclidean. It's a conjecture, we can ask a lot of things. But conjecturally, we think that there should exist a Euclidean dense image. Okay, and so we should have a sort of dichotomy, so which is, I will say that orally, quite unrelated to that one. So if you have a variety which is not of general type, so it has Cadorel dimension strictly lower than the dimension of X, and then these varieties can or cannot be, depending on the cases, of special type. So being of general type is having maximal Cadorel dimension, being of special type is quite unrelated to the properties related to Cadorel dimensions, but what's interesting with this respect, is that Campana provides a theorem which tells us that, so if you take X as above, then there exists a fibration from X to some base, which he calls the core fibration, such that the orbifold base is of general type, in the sense I explained above. and the general fibers are of special type. So if you believe in these two conjectures, then replacing this conjecture, so there is a stronger version of this conjecture where you replace manifold by orbifold in that sense. Okay, that sense. Then the anterior curves falling inside X should cover only a proper subset of C, and in any fiber, in any general fiber, you should have a Zariski-Dens curve. So the description of anterior curves inside X should be very, so the description should be given by this theorem. Okay, maybe you want me to leave that more, sorry. All right. So when we talk about complex hyperbolicity, usually we focus rather on studying that conjecture rather than this one. But I believe they are part of the same moral story, so that's why I wanted to give them both to you. But now I will focus in the rest of the talk on the first one, this conjecture, and more specifically on this conjecture applied to hypersurfaces in PA. So if you apply this conjecture to hypersurfaces of degree D, then we know that if D is right, this that way. So if D is higher than n plus 2, then we know that the canonical bundle of XD is ample. So of course its codirect dimension will be maximal, and so the Green-Griffith-Lang conjecture predicts that there should exist. Sorry, maybe I will introduce some terminology so that will make things a little bit easier. I will write that on this board, sorry. So keep in mind that there should exist a proper subset inside XD containing all anterior curves. And this I will encapsulate in a definition which uses the word hyperbolic. So we say that the complex manifold X is broadly hyperbolic possibly modulo, so I will say modulo Z inside X, if it satisfies this property with respect to Z. So if all anterior curves fall inside Z. And if Z is empty, so there are no anterior curves, we simply say that X is broadly hyperbolic without dropping the module. Okay, and if X is broadly hyperbolic modulo a subset, we sometimes say that X is quasi-broadly hyperbolic or pseudo-broadly hyperbolic. And that is what I will write both. If D is larger than n plus 2, then X should be quasi-broadly hyperbolic. That is broadly hyperbolic modulo subset. And we have an even stronger conjecture, which is not a conjecture anymore. So if you want to drop this quasi, this conjecture due to Kobayashi predicts that you just have to take X general and sufficiently large degree. So if D is larger than some degree Dn, and X is general in its moduli space, then the conjecture predicted that X should be broadly hyperbolic without subset. So there should exist no entire curve inside X. So let me emphasize the fact that general is very important here, since we know that in a Fermat hypersurfaces, for example, so if you are inside Pn and you take any hypersurface given by this equation, you can have hypersurfaces like that with D as big as you want, so that they contain P1s in general. So you want to avoid these examples, and that's why you must take general in the conjecture.
Sorry, what was D?
D here?
D of n? What was that?
Here. So the conjecture predicts that for any n, there should exist a bound, dn, such that if d is larger than this dn, then, and picking x general in the moduli space of hypersurfaces of degree d, this time fixed, then x is broadly hyperbolic. And so that's what I explain now. The second conjecture is not a conjecture anymore. And for the first one, it's not a conjecture if you allow yourself, so replacing this degree by a larger bound, and if you allow yourself to take x general. So, in the past few years, you have had the chance to have very striking results in this direction. So first of all, about the Green-Griffith-Lang conjecture, we had in the last decade the work of Equivariant, Merker, and Rousseau, who showed that if D is larger than some bound, so again, they showed that for any n there existed a bound D1n, such that for x general, for this fixed degree, then x is quasi-Brody hyperbolic. Okay, and so I will write this because it will turn out to be actually the reason why we are here. It's this D1, so they gave the bound, so it was improved after that by many authors, but at this time I think the bound was 2 to the power 10 to the power 5, so it was a large bound. Okay, and about the Kobayashi conjecture, so we had the first proof by Damian in 2015, and then we have different work by many authors. So he showed that if for a different bound you also took xd general, then general in its modular space, then x is Brody hyperbolic, so it contains no entire. Okay, and the bound here, so several people computed different bounds in the subsequent years, and before the work of Gaga and Francis Kirwan, the bound I think was something like n log n or square n to the power n, something like that. And so, using tools that I will describe in a moment, they could show, so I write this here. So using non-reductive GIT quotient, Berger and K1 were able to improve that bound to a polynomial bound. Give a new D1n, drawing something like n to the power 6. And similarly here, you get, of course, a slightly larger bound, but which also grows in the same manner. So the fact that these bounds are close to one another is not a random fact. Actually, it was showed by a work of Riedel and Young that if you are able, using the methods I'm going to introduce, to prove the first one of these results, then you can prove the second one by slightly increasing the bound. Okay, and what are the tools that are used here? Well, they are, as I introduced in the title of the talk, based on jet differentials. So before starting, let me just say that jet differentials were used in all of these works, and so the new improvement that appears here is the fact that, so as I will explain, the methods are based on the construction of jet spaces, and Berger and K1 introduced a new jet space using these non-GIT techniques, non-reductive, techniques, and that permitted to substantially improve the bound. Okay, so let me introduce now the jet spaces. So X here will be a complex manifold, as always. And let us pick an integer k. So that will be the order of the jets we are considering. So we can, using this integer k, define the jet bundle jk of x, which is simply the space of all Taylor developments at order k in x. Namely, you take all germs going from C to x and you quotient by having the same Taylor development up to order k. If you have all the derivatives that are equal up to order k. Okay, and so of course you have a projection to x from this space that takes a germ, or Taylor development, that I will usually write that way, and sends it to its value at 0. And so, if you consider this jet bundle, then you see easily that the fibers are C to the power nk, where n is the dimension of x. But I insist on the fact that it is not a vector bundle, since the transition, the change of coordinates are not C-linear.
Sorry, can I ask about your notation? The
Yes.
C, 0 means the germ of a map? Is it?
This is the germ of C at 0. Thank you. Okay, so this is not a vector bundle. You can write as an exercise the change of coordinates in local charts. And for explaining what follows, I will just introduce a local chart. So if you pick coordinates on some open subset of X, say I pick Z1, Zn, coordinates on some open subset. Then you have coordinates on jku, which is included in jkx, which are given, as you would expect, by the derivatives of these fi. So you have fi prime of 0. So I will not write of 0 if you allow me. f1 prime, fn prime, and etc. until f1 derived k times, fn derived k times. Okay, so this gives you coordinates on these open charts if you add to them the ones on the base. These are the vertical coordinates. And so if you now give weights to these coordinates, which turn out to be the weights given by the reparametrization by C star. So let me give to each fj derived L times the degree L. Then we obtain a graded algebra if you push forward to x the structural sheaf of jkx. Then, so I will write that after that. If you push forward by the projection map pk is structural sheaf, then you get a graded algebra a sum on the degree, and each term of this graded algebra we usually write that way. So where each of these terms is a vector bundle on S. Okay, and so for each k and m, we get what we call the vector bundle of Green-Griffith jet differential of order k and degree m. Sorry, just taking a piece of chalk. And so this vector bundle, we will just in a moment explain that the sections of this vector bundle can easily be written in terms of these coordinates on jk. So degree m, order k. So of course, once you have this, so you have several easy facts related to the links between this graded algebra and jk. So jk is the relative spec of the graded algebra ek bullet gg omega x. And if you now take the proj using this grading, you get the quotient of GKS minus its zero section by the action of C star. And as I said, this action actually is given by reparametrizing F. So if you reparametrize, F like that, and we call that G of T, or lambda of F of T, then these coordinates acquire the weights corresponding to their order of derivation. And so this is this action, which corresponds, yes, to multiply Fik, for example, by lambda k, lambda to the power k. And this we usually call the jet space of Green-Griffith Green-Griffith jet space.
Is there a link between these jet spaces and bundles of differential operators?
So it's quite the converse, actually. So differential operators are given by okay, so this would correspond to the differential operators, but the link is not that obvious, actually. If you have, for example, a jet like that, you can post-compose it with any function on x, and differentiate up to order k to obtain a differential operator defined on the base. But the way these glue when you change coordinate charts is not completely obvious actually. So there is a link, but it's a sort of opposite way of thinking. The differential operators, the holomorphic differential operation we are talking in the title of the talk are given by the sections of these vector bundles. And so not by that one. All right, so as I said, this jet space here, this is the Green-Griffith jet space of order Q. All right. And so, why is it useful in hyperbolicity? Well, it comes from a very important theorem, which is at the base of the theory, actually. Maybe two. Which we usually call the fundamental vanishing theorem. And which I will state just now. So, theorem. So, it can be attributed to different authors, but I think we can simply say Suegan and Domailly. So, this theorem tells us the following. So, pick P, a global section of this vector bundle that vanishes along an ample line bundle, or an ample divisor. Let now F be a holomorphic map from C to X. Non-constant, if you want. It will be trivial if it's constant, actually. Then, and this I will explain in a moment, you can apply P if you see it as a differential operator to F. And you get something like that. So I will write it that way. So P, as I will explain in a second, can be expressed as a differential operator that you can apply to any germ of curve. So I think you can guess that will be true using the fact that P can be written in terms of these coordinates. Then the theorem tells us that this is identically zero. And just to clarify this, I would just say that in local coordinates, you can write P under a form that you can right away apply to F. Locally, P of F and all its derivatives up to order k, well, this is none other. So this you can see as a function on C. So you apply it to some parameter t that lives in C. Another point t, well, this is given by a product in all the derivatives with some powers. So this is quite fun to write, so I will not spend too much time on that. But you have products of functions like that, up to order k, up multiplied to some powers. Lkn. And so this is a product, and you sum that. So, okay, this is not that nice to write, but I will write Li, the sum of all Lji, and the condition on the sum is the condition which is given by the fact that this has the degree m. And if you write that down, you get L1 plus 2L2 plus 3L3 plus KLK equal to m, and you have such monomials, and in front of them you get a holomorphic function on the base that you post-compose with f that falls inside x. Okay, so this is a differential operator that can locally be written that way and that you can apply to any entire curve. And the theorem tells you that if this vanishes along a number line bundle, then it is identically zero when you apply it to F. So this gives strong restriction to entire curves inside X.
Excuse me.
Yes?
So in fact, when you write jkx equals spec on the right,
Yes?
spec of that,
So here, so assume you are in the algebraic setting, X is a projective variety. You can have local charts on X, which are affine charts, and even small enough that you have coordinates on that. And then, when you take the spec, I mean that fiber-wise, you take the spec of the local, of the ring generated by this. So this is the ring of C generated by F1 prime, Fn prime, up to Fn derivative k times. I give the degree L to each monomial derivative to order L, and you could take the spec of that. So the degree here doesn't matter actually for taking the spec. And the fibers of Jk are just this spectrum. So it doesn't matter, you get back C to the power nk actually, as you see. You have nk coordinate. So this is a relative spectrum, and you can get the space on which you had this sheaf of functions back from taking the spec actually.
but, I mean, if the push forward of the structure sheaf is that graded ring, shouldn't then jkx be spec of that graded ring?
Yes, so that's why I put a bullet here. Maybe that's your question. Sorry,
That's
no, it's not a zero. It's you take the sum of all M.
Okay, great.
Okay, that was your question. Sorry. Yeah, wasn't very clear for my part. So, okay, I cannot prove this vanishing theorem, but I can give you a moral, but it should be true. Imagine that C is given by an elliptic curve. E elliptic. And so your entire curve would be given by the composition with the universal curve. Then P, I will take more space. Okay. So assume you are in this very specific situation where C is given by post-composition with an elliptic curve. Then P here is inside this space as a section of this vector bundle over X, vanishing along A. And here you can pull back this section to E. And what do you get? You get a section that lives on E, elliptic curve, of, so there are several E's, sorry for that. Okay, so E here is the elliptic curve, and this is the Green-Griffith jet differential of section of differentials of degree K and order M on E that vanish along the pullback of A on that elliptic curve. But this, as you can easily see, this is a trivial vector bundle on E, since E has a flat coordinates, and so the change of coordinates are very trivial once you derive this flat coordinate. And so you get a section of a trivial vector bundle vanishing along an ample line bundle, and this is zero. Okay, and morally, so you can easily see that it works also if you replace E by P1. So for non-hyperbolic projective curves, the theorem is trivially true. And this theorem tells you that actually it still works if you replace this non-hyperbolic curve by a transcendental curve starting from C. sorry.
So you gave us the idea if you have compactness. What happens if you just have an entire curve?
So what you have to do actually is to, so there are several ways of proving them. Well, several increasing case of difficulty. So for example, imagine that all these derivatives are bounded. So in that case, what you can show is actually you can reduce to the fact that this will give you a function on C, which will be bounded and vanishing at some point. So it has to be constant and then it vanishes. And so the difficulty is to control the order of growth of the derivatives, and that is usually done using Nevanlinna theory, which is the theory which controls the growth of functions, especially derivatives of functions on entire curves, on the C. But there is, as I said, a very an easier case where you assume that f prime actually is bounded in some Hermitian metric, and then using Cauchy inequalities, it will give you bounds on all the derivatives that have to happen after that, and then you get, when you pull that back to C, a bounded function that vanishes at some point.
Okay, thanks.
Okay, and now what I want to do in the last 9 minutes is to explain what was actually done in this work of all the people that have written on that board, and that eventually culminated in these results, and how were jet differential used in that. So I will not be able to prove anything, and even less maybe state a true theorem, but Sergei will explain that in more details tomorrow. Okay, so I want actually to rephrase this theorem in a slightly different way. So pick X and the Green-Griffith jet differential that lives, sorry, not differential, but jet space that lives above it, and assume that you have an entire curve. So what you can do is to lift this map using, so you see that this is actually a quotient of jk minus 0, and minus the, okay, I will write maybe a little bit complicated diagram, sorry. But what you can certainly do is to lift the map from C to X to jkx, and then outside of the set where the jet vanishes, you get a well-defined map towards that space, and so you can complete the map at the point where the jet vanishes to get a well-defined lift, which I will call Fk. Maybe it's changing a little bit the notation I used before. Okay, so you get such a lift. And how can we rephrase this theorem? Actually, on xkgg here, we have a tautological line bundle which I will denote OK1. So it's not truly a line bundle, it's rather a stacky line bundle or Q line bundle, since actually this has as fibers projective, weighted projective spaces. So you can either talk of sheaves when you take powers of this, or stacky line bundle, such that if you pull, I will also use the notation pi k if you allow me, such that if you push forward these sections, you get the Green-Griffith vector bundles. And so what does this theorem tell us actually? If you want to rephrase things using this diagram. Then, what it tells us is that if you take the image of C by that map, then it falls inside the intersection for any m of the base locus of the nth power of k minus the ample line bundle on the base. So any section of this will give you a jet differential like that, and the image of Fk will fall inside the zero locus of this. And this, you can, if you know this terminology, you recognize the augmented base locus of this tautological line. So now, what you deduce is that the image of C falls inside the projection on the base of this augmented base locus. And this we usually call the Green-Griffith locus of order K of X. And so what was done actually in this work of Equivariant, Merker, Rousseau, Damian, and eventually Bergziker-1 is that they showed that under their hypothesis, in this base locus, so all these people for hypersurfaces as before, they showed that the Green-Griffith locus, so in this case it's order n, is either different from X or empty, depending on whether you are trying to prove Kobayashi conjecture or the Green-Griffith conjecture. And so this was for under the hypothesis I stated at the beginning of the talk. And so if you are able to prove that, then you are done, because the F will fall in a locus which is different from C, from X, or in the second case, there will not exist any of that. All right. So to finish, I will just say a few things about the need to use equivariant things, because actually the spaces that were introduced were not these spaces, sorry, xk Green-Griffith above, it were not the spaces that were used in that work. There were different spaces. So, linked to the fact that if you have a map from C going to X, then actually, as you see, the lift above depends actually on the parameterization you chose for F. So it depends on whether you are considering F or replacing it by F composed with psi being by holomorphism of C. And so what you prove these results, actually, it is much better to work in an equivariant way under the action of these maps. And so I will just finish with that. The fact that on the space JK I introduced before, there is a group that acts, and this is the group that we call diff_k, simply diff_k, say, which is the group of bihomorphism of the germ of C at 0 up to order K. And this group is highly non-reductive. So I think Gage will give you tomorrow formulas that explain that fact. But if you have this group diff k, then you have a reductive quotient which is just C star, which is given by sending such a diffeomorphism to its derivative at 0. And you have a unimutant radical which is actually the main source of a problem in this theorem. And just to finish, I would just say that one would like to have as a candidate for the jet space things are usually done by replacing xk jj, which was actually, you can see it as a quotient of jkx minus the zero section by the C star that appears here. By something which would be the quotient of the same thing, but by this group diff k. And so, so there were several candidates for this jet space. So the one that was used by many people before the work of EMGW01 was a construction which was due to Demailly, which gave actually a compactification of the locus where this action has a good quotient. So if you have an open subset inside that, which is actually given by the jets with non-vanishing first differential, on which this has the good quotient, and the question was to compactify that space. So Demailly gave a candidate, and so if you replace in all the story I explained before that space with this new one, which was constructed using non-reductive GLT theory, then Gagai will explain tomorrow that things work in a much better way. You can improve the constant substantially. And so, yeah, I think I will stop here. So thank you for your attention.
Any questions?
Yes.
Yeah, let me start with asking, you start with an entire curve, right?
Yep.
How does this story change when the domain is not C but any open?
So there are many works in this direction. So for example, what you can do is replace C by a cover of C. So you can have X here, and here something which starts from a Riemann surface with a ramification. And so the question is, well, what condition can you impose on X for such map not to exist, assuming that you have a way of controlling the ramification. So if you assume that the ramification is not 0, the conjecture predicts that X of genotype should imply that there are no such maps outside some locus. And now we have, using, for example, Nevanlinna theory, ways of saying that you have R with small ramification. And then you can extend the theory to maps from Riemann surfaces with small ramification above C, and states results in this direction. Hyperbolicity results in this direction.
Right. The reason why I'm asking this is, so if you replace X by a symplectic manifold, and you just look at the J homomorphic curve from some Riemann surface, then this Campana's conjecture looks like that you look for a Gromov-Witten type quantity to not vanish, because you're asking that there is this function existing, going through, having a dense image. So you're requiring that it's passing through a generic point in the target manifold.
Mm-hmm.
So is there like any way exploring this direction?
This is a very good question. So in symplectic geometry, I know that people are trying to find curves which are related to the symplectic geometry. So I am not aware of to which extent we can push the analogy towards these two theories, but certainly. So, for example, what you a thing I have not said, for example, is that varieties which have a trivial canonical bundle are of special type. And among themselves, you have these holomorphic symplectic manifolds. So somehow I think there are many ideas that are related, but I'm not sufficiently aware of what is done in symplectic geometry to give you a true answer. So.
Any other questions?
Yes.
Yeah, go ahead.
Is there a conjectural bound? What you expect in the covariance
Yeah.
shape?
So conjecturally, so maybe I will be slightly off by 1 because I have not chosen the. So here we expect 2n plus 2 as the best optimal bound, and for small values of n it should be even better. But you have results by Zeidenberg which give you precisely the bound for which it should fail, actually.
The definition of this Green-Griffiths locus here depends on the choice of an ample line bundle?
I don't think so, because here you see you have this augmented base locus, which does not depend on this ample line. It doesn't depend on the choice of A. And so, one thing I should say, two things actually. So the fact that there exist sections of this line bundle is equivalent to X being of general type. So this is a very striking fact. The fact that this theorem is not empty tells us something is equivalent to the fact that X is of general type. So this is a theorem of de Mailly. The existence of P as above. So you have two directions, results of de Mailly and Campana-Pound, which tells you that the existence of P as above, outside non-zero of course, is equivalent to X being of general type. But it's quite possible that even for hyperbolic varieties, all these locus, all these loci are equal to X. So the strategy could completely fail, even though we are other means of saying that X is of general type and hyperbolic.
Any other questions? If not, let's thank Benoit again for a very